All right, now that we've done one-dimensional motion, we have to combine this into two-dimensional motion. Good news, you already know how to do this. It's just going to be our kinematic equations in x and our kinematic equations in y. We're going to treat each motion separately. The equations of motions we previously used still work. We'll divide it into x, the horizontal motion, and y, the vertical motion. If we needed to get a third dimension, we would call this z. It would be perpendicular to both x and y. Until we get to magnetism, we won't have to do that. So, we're going to deal with exclusively the type of motion called projectile motion. This is the motion of an object that's moving near the surface of the Earth, and it will only act under the influence of gravity. In fact, that's how we determine if projectile motion is occurring. The two key traits for projectile motion will be that there is no acceleration in the x direction. That means a sub x is 0. And in the vertical direction, or the y direction, the acceleration will be due to gravity, meaning that a sub y would equal minus g. The only other real mystery that we have to worry about are the initial conditions. Usually, the object is going to be launched at some sort of angle, and so we're going to have to use trigonometry to break that apart to figure out what our initial x velocity and our initial y velocity would be. We'll always make it so the angle is above the horizon, and it's going to be between 0 and 90 degrees. Here's where we need some of the trig that we used before. So here's a vector representing the v initial. There it is. It's an object that we're going to launch with at some particular angle. Here's the angle that we make with respect to the ground. We need to resolve this vector. We know how to do that. We need to break it into an x piece and a y piece. There's the x piece. That's the adjacent side. That's going to be vi cosine theta. Oh, and there's the opposite side. That would be the y piece. That's going to be vi sine theta. If we do the math that we know here, we know that the v initial x is vi cosine theta, and the v initial y is vi sine theta. These are the initial velocities we use in our kinematic equations. They'll change as time goes on, other than the x velocities we'll talk about, but you'll see that they fit into our kinematic equation. How about the initial locations, either x sub I or y sub I? Usually, as we've discussed in the past, unless I or the problem tells you very specifically otherwise, x sub I will be 0. Y sub I, however, can be different. Just like in free fall, you're going to define the initial y as the starting vertical location. If you start on a cliff, that's a positive number. If you start in a hole, it's going to be a negative number. If you start at ground level, then it's going to be just 0. So here's a cliff with a particular yi that's going to be positive. Here's a hole with a yi going to be negative. These problems are not difficult to solve, especially if you manage to keep the x and y motion separate. Here are the 6 equations you'll use. Top line, describing the acceleration, describing acceleration defines projectile motion. We'll use the velocity and the distance or height equations to find things of interest. So here are the equations. Notice what we had here. Acceleration in the x direction, 0. Acceleration in the y direction, minus g. My initial y velocity, or my initial x velocity, sorry, vi cosine theta. My initial y velocity, vi sine theta. Notice in the velocity equation for x that my final x and my initial x don't change. I have no acceleration in x, so that means my velocity stays the same. It doesn't speed up or slow down. Notice, however, in the vertical direction, it does change. That's because of gravity. On the way up, the thing slows down. On the way down, it speeds up. So our v final y as a function of time is going to equal vi sine theta minus gt. The x distance, xt, is equal to x initial plus vi cosine theta times t. Notice that that's linear in there because we have no acceleration. And usually the x sub I would be 0. Similarly with the y sub I, or the y final, I got y sub I plus vi sine theta t minus 1/2 gt squared. This is quadratic. It will be curvy. I typically divide projectile motion into 3 different types. We'll deal with type 1, type 2, and type 3. I'm going to deal with a type 1 first. Just be aware that these distinctions, type 1, type 2, and type 3, are my names. I've never seen a physics book or anywhere else use these things. I just try to divide them up to make them a little bit easier for you guys to understand. Type 1 is the problem that has symmetry in it. The projectile starts and ends at the same level, usually ground level. This is very similar to the free-fall problem where you started and end at the same level. Remember, in those cases, your time of flight was twice your time to top, and your final velocity was negative your initial velocity. We'll discuss those in a second. Remember, in projectile motion, the object never stops moving. There is always motion in the x direction as the x velocity is constant. The y velocity will change. It starts positive, reaches 0 at the top, and then becomes negative on the way down. We can calculate time to top, TTT, by setting the v velocity equation equal to 0. Here's the equation. TTT is equal to VI sine theta divided by G. This equation for time to top will work for all three types of projectile motion, so it's a good one to keep handy. Notice that if you make your theta equal to 90 degrees, this equation becomes the free fall equation we had. It's where you throw a body straight up in the air. More on the type 1 problem. If I take my time to top and I plug it into my y equation, I get y max. There's my y max. Y initial plus the quantity vi sine theta squared all over 2g. Usually the y sub I is 0, but pay attention to what they ever give you in the problem. This equation for y max will also work for any type of projectile motion problem. So the time to top and the y max are valid for all three types. For type 1 problems, because we have symmetry, time of flight is very easy. I just take my time to top and I multiply it by 2. It takes the same amount of time to get to the highest point as it takes to fall back to the ground. Range is something new. Range is the value that x takes on after the time of flight. We'll just take the time of flight value that we calculate and plug it into the x equation. So range will equal x initial plus vi cosine theta times your time of flight. Again, your x sub I is usually 0, but just pay attention to that. Finding the final velocity vector is also easy. Since there's symmetry, your v final is the same as your v initial, except that the angle is below the x-axis instead of above the x-axis. So your v final will equal v initial at an angle theta below the x-axis. Just a couple of additional facts about type 1. Here's another equation you could use for range. It's a little bit different. Vi squared over g times the quantity sine of 2 theta. Look at that. You have to take your angle, multiply it by 2, and then calculate everything appropriately. It's a special equation. It works for only type 1 problems. I like the other equations I've given you earlier. They just make a little bit more sense to me. But I want you to note something. You can get the same range for two angles between 0 and 90 degrees. Any two complementary angles, those are angles that add up to 90 degrees, will give the same range. So, 10 degrees and 80 degrees give the same range. 20 degrees and 70, 30 and 60, and so on. They would all give the same range. This also means that 45 degrees gives the maximum range. Makes sense. If you think about an angle of 90 degrees, that's straight up, so the range would be 0. It would hit you on the head. If you think about an angle of 0 degrees launching horizontally, it's going to hit the ground right away. Well, what's between 0 and 90 to give you the maximum range? That would be 45 degrees. Type 2 problems. Here we're going to launch from the top of a cliff with a horizontal velocity. Here's my cliff, there's my object, I'm launching it vertically. I've got an initial velocity, I've got a height h. Notice that the initial velocity is entirely in the x direction. That means my v initial x is just equal to my vi, and my v initial y is 0. In the y direction, for all practical purposes, the object is falling from rest. For a type 2 problem, since you're already at the top of the hill, it doesn't make a whole lot of sense to talk about time to top or y max. You're already at the highest point, so your y max is your initial y, and your time to top is 0. So we typically don't calculate these for a type 2 problem. To find time of flight, I need to set my y equation equal to 0. My y final will be 0 when it hits the ground. Since my v initial y is 0, we get this equation. 0 equals h minus 1/2 gt squared. This is easy to solve. If I solve it for t, I find the time of flight for a type 2. It's equal to the square root of 2h over g. Continuing with the type 2 problem, once I have the time of flight, I can find range. I take my x final equation and I plug in the time of flight for t. So my range would be vi times the quantity, the square root of 2h over g. I can use the vi for the type 2 problem because the v initial x is equal to the initial velocity. I can finally find the v final vector. It's a vector. I have to express it both ways as an x and y and an r at theta. I have to use my v final x and my v final y equations for getting this. I get that my v final x is equal to my v initial, and my v final y is going to equal minus g times the time of flight. Remember, my initial y velocity would be 0. Some things to remember about these things. Time of flight is completely determined by the height of the cliff. Nothing else matters in the problem. If I would shoot something twice as fast from the cliff, still horizontally, it would land further away, but it would still land at the same time. I give an example. Twice the initial velocity means twice the range, but exactly the same time of flight. Secondly, I typically don't define time to top and my y max because I'm already at the top. I'm just kind of telling you information you already knew. So let's try a type 2 practice problem. Let's say we launch a cannonball with a velocity of 125 meters per second horizontally off a cliff with a height of 225 meters. I want to find the time of flight, the range, and the v final. Time of flight's easy. I plug it into my equation, a square root of 2h over g, so that's 2 times 225 over 10. I get 6.71 seconds. Notice that my v initial did not come into play to find the time of flight. The only thing that matters in this case would be the height of the cliff. To find range, I take my v initial, that's my v initial x, and multiply it by my time of flight. If I do that, 125 meters per second by 6.71 seconds, I get 839 meters. Finally, I want to find my v final. If I put the numbers in, I find that my v initial, my v final x is equal to my v initial x, that's 125. I put in my time of flight for my v final y equation, I get 0 minus 10 times 6.71, or minus 67.1. So my vector becomes 125, comma, minus 67.1 meters per second. Don't forget units, don't forget the minus signs, do everything right. Untrigonomifying that gives me a vector that's 142 meters per second long and an angle of 28.2 degrees below the x-axis. Let's try a type 3 problem. I already got the ball in the picture. You're going to start on a cliff and you're going to be launching your angle at some non-zero positive angle. So there's the angle, there's my initial velocity. There's the height of my cliff. Now I need to do the trigonometry. I need to break the vi into the v initial x and the v initial y. Remembering the trig that we did before. V initial x will equal vi cosine theta. V initial y will equal vi sine theta. Pay attention to the y initial. If my y initial is greater than 0, I'm on a cliff. If my y initial is less than 0, I'm in a hole. Time to top, same way. Same equation we used all of before. Everything works here. Y max, same thing. Works from before. Same equation we have, but now your y initial is not going to be 0. I want to continue. Now we come to the hardest part. I want to find the time of flight. Time of flight is difficult because it involves a quadratic formula. There's no symmetry. That means your time of flight is not going to be twice your time to top. Don't make that mistake. You have to solve the quadratic equation. To find the time of flight, I have to take my y final equation and set it equal to 0. Remember, y0 or y final equals 0 is when my object finally hits the ground. So here's my equation. 0 equals y initial plus vi sine theta times t minus 1/2 gt squared. My a is going to be minus 1/2 g. My v is vi sine theta, and my c is my y initial. You should have the quadratic formula written down somewhere. You should know how to use it. If your y initial is greater than 0, I'm going to get two answers for t. One of them will be positive, and one of them will be negative. You got to ignore the negative time. If my y initial is less than 0, I could conceivably get two answers for time where they both would be positive. The first positive time happens when my object is coming out of the hole and reaches ground level. It keeps on going up, reaches its top, and then finally comes down and hits the ground. So the second or longer time would be what we would consider the time of flight. Let's finish up. To find the range, I have to plug my time of flight into my x final equation. We know this equation before. It's pretty much the same one we've had. Again, my x initial will typically be 0. To find the v final vector, I have to find my v final x and my v final y. I use the kinematic equations I know for these. So my v final x is equal to my v initial x. My v final y is going to be vi sine theta minus g times the time of flight. After I find the v final in the xy form, you have to untrigonomify it. Let's try an example. I have a projectile launched from the top of a 216-meter cliff at a velocity of 75.4 meters per second at an angle of 32.1 degrees. I want to find time to top, y max, time of flight, range, and v final. Time to top, same equation we used all along. Just put the numbers in, plug and chug. I get 4.01 seconds. Y max, same thing we did before. Don't forget to add the initial y max, in this case 216, or that'd be the yi, sorry. You put it in there. I find that it goes 80.3 meters above the top of the cliff. Add that to the 216. I find that my maximum height above the ground would be 296 meters. Now we got to find time of flight. 0 is equal to 216 plus 40.1 t minus 5t squared. There's my c value of 216, my b of 40.1, and my c of minus 5. I find the two times to be 11.7 or minus 3.69 seconds. Make sure you pick the positive one. Make sure you can duplicate my results. This is going to be one of your FRQs. You're going to have to know how to do it. Again, I ignore the negative time, so my time of flight here is going to be 11.7 seconds. Range is a straightforward calculation. I take my x initial plus my vi cosine theta times time of flight. My x initial is 0. I put in my numbers. I find that I land 747 meters away. Now the v final is a little bit more difficult, but not impossible. Putting in my values in my equations, I find that my v final x is 63.9 meters per second. I find that my v final y is going to be minus 76.9 meters per second. That should make sense. My x is still moving horizontally. My y is moving down. So I should get a positive x value and a negative y value. I get the vector 63.9 comma minus 60 or 76.9 meters per second. Again, don't forget the units. If I untrigonomify that, I get a magnitude of 100 meters per second at an angle of 50.3 degrees below the x-axis. Again, make sure you can get these results. These are the types of problems I'm going to expect you to do. Good luck. Time to practice.